So, good morning and thanks for the invitation. So, I'm going to talk about TLS and TLS. And TLS is of course the de facto protocol for securing application traffic on the internet. And these are today actually surprisingly widely deployed in devices, for example, on the smartphones and custom-based thinking today. So I thought let's look at on a high level what happens if you put these two together with the add double or not. And the benefits of doing this are of course quite obvious. You can use P to make TLS endpoint more secure, and on the other hand you can use the P can use TLS to communicate securely with the outside world. And there have been some attempts in the past to integrate these two, but it's nothing permanent came out of that. So maybe with this standardization we will see the final getting of these two. And I would like to say a few words about the workplace where I work. It's called Helsinki Security Lab. It's part of Huawei's Finland research center. We do research and so-called advanced development on platform and system security topics. And there are many former Nokia employees there. Actually, one of the few ones that doesn't have any Nokia background. And because of this, Nokia guys, the lab has significant TE expertise because Nokia was kind of pioneer in the early TE development in the mobile domain. And we have made a lot of contributions to Huawei's TEs like iTrustD, and we have representation in the global platform TE related working groups, and now also in this Linux CCC. And what makes it interesting is that when I came to the lab, I had didn't know much about TEs, but I had significant experience in TLS implementation. So this kind of expertise kind of joined. And when I had these TE guys immediately found TLS related tasks for me. They said you can use TLS for this and that, like enclave migrations, for example. And I think this highlights nicely how TLS can be very useful for TE. And I probably don't have to say much about TLS. It's the world's most widely used security communication protocol. It's now used in top of TCP. And you can see the TLS handshake on the right. And you can say that it's kind of 1.5 round trips of handshake on top of TCP before you can the participants can start sending application data over the security channel. And the motivation for TLS was to secure the credit card-based purchases in the web browser in the early 1990s. And the first 3 versions were developed by Netscape. The third one was the first serious one, you could say, was developed with some help from crypto experts. And in 1999, IUPF took over the specification from Netscape, and it was renamed from SSL to TLS. And as you can see from the slide, there have been there is a long history of attacks and reactive fixes, and that was one reason why it took so long to develop this 1.3 version. There was 10-year gap, because now they wanted to do a good job with the design and the program against that just reactive. So now they created a version that consensus seems to be that it's actually quite secure. It's been formally verified. There have been some attacks against some features like this zero RDT data, but the common here is that it is now mature and secure. And the trusted execution environment other part is applicable. So you can define it in many ways, but one way is to say that it's a set of hardware and software features that together provide readings and automatic execution of code, protected storage, and that's important for us is that ability to convince remote verifiers, for example, your code is really running in a PE and PE is secure. And you can very roughly classify the hardware into three categories. There's this external secure core processor like HSM, for example. Those are physically separate from the main system. And the embedded secure core processors like the TPM is a part of the main chip. And then there are these processor secure environments where the T is actually part of the main CPU. And that has the benefit that can in general as part of the main CPU, and it just is flexible with what it can do. And there are two architectures for these PSCs, strict mode architecture like Rustron, where you have two modes inside the main CPU, secure and normal mode. And then there's this enclave architecture where you have multiple Ts in the same device. And the HSM, according to this definition, was that the first T and the motivation for HSM was to protect the military communications and finance like these automated teller machines. And then in the early 90s, GMB invented this SIM card, and the commercial motivation was, of course, to protect the mobile subscriber identity and the related keys. So there's no illicit use of the network, mobile phone network. And then you notice we got the trusted platform model. It's like HSM can be used to secure keys, but in that it does a little bit more. Because, for example, that is put and sealing, and now it's in all new laptops because Windows needs it for BitLocker thing. And then this processor secure environments were first developed in the mobile domain. Ancient and custom were the first ones. And the commercial motivation for those was for the subsidy lock that you bought the device and it was bound to a particular mobile phone network subscription. They needed a tamper-proof device identity for that. That was the main motivation for this PEs. And CMD's Mobico was probably the first like software implementation of this Rustron like this. And then in 2015, we got the Internet Jets for PCs and servers. It kind of got an explosion in the PE research. Hardware was like easily available for experiments. And then in recent years, we have had this confidential computing paradigm. This essentially TE is in the cloud. It trend that TE protects entire virtual machines. And so, when I said that there are two benefits when we bring this couple together, the one was that TE can make TLS more secure, and that's all pure from Seems travel that's been used many times, so it fits the story so well that let's use one more, and we can modernize it a little bit by saying TLS is the encryption and instead of credit card information, we can say secrets and confidential cloud workloads, for example. And the meaning of this is, of course, that even though the communication itself is secure and you trust that on the partners and authenticate him, if his environment is completely insecure, then you're not going to get much security. It stores these keys on the partners and does data processing on the partners, and then attackers can easily get those. So when I said there are three categories of this TLS. First one was this external secure co-processor. So let's look at how we can integrate TLS with that one. So the HSM was the third, and then the SIM card is also one. It's typically not used with TLS, but these electronic identity cards, they have a private key and certificate. They are actually used to protect TLS private authentication private keys. So let's use HSM as the example, and we can use the HSM like this. We integrate it with the TLS endpoint authentication. The endpoint authentication works so that you send your public key certificate message, and then in this certificate verified message, you prove that you have the corresponding private key. Now we can put that private key into the HSM and compute this certificate verified signature. We can use this common callbacks in most TLS libraries. So, for example, the OpenSSL engine framework to invoke the HSM to compute the certificate verified signature in the key. So now we can use the HSM to protect the endpoint validity, but the issue is that the application data is still processed on the park bench, so to say, so it's not secure. And there's also no proof that the other endpoint is in a secure state. Now we come to the second category of the embedded secure co-processor. And here we use TPM as the example. And we can integrate TPM with TLS like this. We do basically the same thing, that we put the private key inside the TPM and use callbacks to compute the verified signature. But now in addition, the bootloader can collect the measurements of the software that's putting on the device and store them in the TPM. The TPM can attest to these measurements by signing them and encoding them in this TPM pure attested evidence. And a typical way to transmit that is inside the certificate, that it's as experiment extension, for example, that's computing group is one extension for this. So now you get some guarantee that the endpoint is running the correct, or at least put the correct software, so we get some endpoint security guarantees, but the application data is still not protected. So now let's look at the third category of DDD is processor secure environments. And like I said, they were first developed in this mobile domain and protecting the radio frequencies and the subsidy-locked weather ranges, motivations, and the vendors also didn't want to increase the bill of materials by providing including other TPM like sitting on the device. So this MCL and class software code were developed with Nokia. And because this PSC is that is kind of inside the main CPU, it means it can be quite flexible and run complex code. So now we can actually put the whole TLS endpoint inside the PDE. So now we get protection for the keys and also for the data. And we can we still need to use attestation to prove that the PDE is secure, of course, and we can transmit attestation evidence inside the certificate message, for example. I'm claiming that these two make a happy couple, and we saw three ways to integrate them. There are of course many other ways. TPM, for example, can be used in many other ways, and especially TPM 2.0, you can do quite complex stuff with that. But I think these three integrations are kind of represent the deal. And now let's look at the second benefit that the TLS can help TDD to communicate securely with the rest of the world. And there are essentially two kinds of communication with TDD. is. One is provisioning, of course, of secrets like DRM, these or confidential cloud workloads or large language models. And then there's service access, like during the large language model or really sophisticated banking app, then it might have its own TA that is stored to the backend to do transactions. And for this communication, you of course need interoperability, and that means standards. And I mentioned this banking application. I think most don't actually write their own PA. Instead, they use this Android PCM API, and they use the Android keymaster PA to store some secret keys. So that's kind of standard way to use, and common way to use PAs in Android. That you use the keystore PA to store the secrets. And the first standard for the is always this global platform, which is widely followed by the mobile vendors. I think most smartphones in the room probably have a trust on the that's at least mostly global platform compliant. And for this provisioning, they have this TMF and OTRP protocols for provisioning keys into the PS, and then for the service access communication, they have the socket API, where I have been the editor recently, and in one we added support for TLS 1.3, and in 1.2 we added support for attested TLS, and then approach that we took is that this is only about specifying the APIs. We want to specify an API that the TA can call to use attested TLS, and since there's no standard protocol for that, we can for now use custom TLS variant beneath the API, and later when we look at the standard, then you can change the implementation under the hood, and API will remain the same, and we don't have to change the TS. So that was the idea of this one to this is now finished in public review. And currently we only support client-side sockets and client-side TLS. So maybe adding server-side support for server-side TLS would be the next step. And then in the confidential computing domain, I think there are I'm not aware of any like standards for TEs there, but instead we have these projects in the Linux system like Verizon, for example, which kind of try to harmonize some aspects of confidential computing in this kind of project way. And there's this idea of draft on attested TLS, which I hope will standardize the protocol. So with these three developments, these TLS and TE timelines kind of merge, and hopefully for good. And integrating attestation into TLS is a really important topic, as also covered by Carsten's talk. So, of course, you don't want to modify the core protocol too much, and you want to be efficient and avoid relay attacks, and those will continue to use with attested TLS with the existing TLS libraries. And I have found it quite useful to split the approaches into pre-handshake, post-handshake, and inter-handshake approaches, depending on when the attestation evidence is signed, before the handshake or during the handshake or after you have established the TLS session. And my opinion is this inter-handshake is the best one, at least if you have to pick just one, because there's no extra boundaries like Arto said, and it works well with existing TLS APIs. You basically just need a configuration step before you use the existing APIs like SSL, write, and read. And it turns TLS into a hard-tested and secure channel, so there's no intermediate phase where you have the channel that is secure but not attested. But you will have it if you use post balancing and do attestation on top of the TLS session. And actually, there's a fourth way to you can do attestation even before you have any knowledge that you are going to use TLS later. You can do it as part of the certificate issuance protocol, and this, I think Hannes Talk will have some more on this approach on this CSR thing. So as a summary, I can blend this to now kind of mature. So TLS 1 and 3 is finally regarded as secure and is formally verified. And those PEs are quite widely deployed and even standardized based on the mobile domain. So I think they will make happy couple, and the benefits are quite obvious. Of course, like in every marriage, you have some challenges. For example, I think this integration of channel binding and remote attestation is not yet fully solved the problem. For example, I like to use the TLS exporter mechanism to derive the channel bindings first. Then you can use that's what it was meant for, and you can embed this in TLS library APIs to get the important value, but in Carsten said that they if to correct a different approach, that they kind of send the transcript has to also cover the different element shared secret. That's also an interesting way to think of that. So maybe we still need some work to study all the possibilities that we have and what are the security implications, and also what we do with some TLS features like vision and sakes, which are aggregated and don't have this certificate verified messages that we can conveniently use to transmit the evidence. And then what about PKI? TLS and PKI have been kind of close friends for a long time now. So we'll add this replace PKI or we'll add this part of PKI, or will they work it beautifully somehow? We still need to do some work on that. And as Samuel said, this both two are now mature adults and quite old and established, so it's time to settle down and be still together for good. And hopefully these standards will help with that. So thanks and good questions.
Questions? So while others are thinking, on the slide we had the categorization, I like the whole spectrum of the teams. But don't you think that it's a very broad kind of a definition of TD, starting from TTM, HSM, everything within the definition of TD?
Yeah,
Would you say it's kind of very broad definition of the TD?
Yeah, it is very, very broad. It's useful in this context, so it will show the full history of this field.
Right. So that tested TLS can apply to all of them. That was your kind of good.
Yes.
Yeah, because we like that.
Arto, I thought I saw you mentioning that the tested TLS is supported already in the Total Platform Socket API. Did I read that correctly?
Yeah, it is this 1 or 2 version.
Okay.
That was recently in public review, and now the review is finished, and I think we will probably publish it quite soon.
So just to clarify, one is the role of transforms and those two versions.
No, yeah.
This is one thing.
That's so there's just about APIs and it's highly of drafts about that protocol itself.
So let's say the speaker will also be this one make one small comment. You mentioned Nokia more than Huawei in the slides.
Yeah.
I'm just thinking, all the Nokia TV experts are in this room, and none of us work for Nokia. Anyway, just a. So let's thank the speaker once again, very interesting. Thanks.